How we doing? Welcome back. So let's take this ball. It doesn't matter. It doesn't matter what object you use. But if this thing here, let's just say that right here, imagine this plane right here. This is an X. If this thing is kicked, it's not going to go just straight up, and it's not going to just go straight along an X. We know that actually it's a mixture of the two. So you need to start thinking about seeing everything in an X and a Y coordinate system. It's actually, as you already know, it's going to take a path that's kind of like this. It's going to arc up and then it's going to come back down until it hits back at ground zero. And along that path, we can evaluate both the x and the y components of that projectile along its path, and we're going to find out that when it gets to the top of its path, the bottom of its path, wherever we're looking at, that there are some dynamics due to the fact that acceleration due to gravity is constant. Those dynamics stay constant as well, and it helps us to better properly understand our projectile motion. So let's jump in and take a look. This is just sort of a standardized concept for velocity and displacement for projectile motion along that path. Let's take a look. Welcome back, everyone. We've already taken a look at a projectile, just the dynamics of launch horizontally or launch at some angle theta. We're going to be taking a look at some angle theta, but we want maybe something, we want to look at that a little bit more. Instead of being up on a ledge, let's look at the fact that we're on the ground and something is launched at an angle, and we know that it's going to take this path that has that arc, right? So let's get our angle, let's get our ground. All right, we got our ground. And then let me get back off of this tool here. So we've got this object here, and this object here is launched at some angle theta, right? So, and that's a pretty sharp angle, but that's just to illustrate everything, right? So you already know that this thing, when it's launched, will take a path that's something like this, right? This is nothing new. I haven't taught you anything new yet, all right? And I may not even teach you anything new on this video. Who knows? Well, we know there's going to come a time where this object is up here at the top. All right. So now what we can do is ask ourselves, when it's up at the top, what has happened? First and foremost, before we do anything, what I want you to do is be able to see that we have essentially a right triangle right there. So we have a y at the halfway mark of where this thing was kicked. We have a side that is opposite of angle theta, so we can do some evaluation here. Okay, we can do some evaluation. All right. So since we know at that point, once this thing is off the ground, the y component is going to be what we've always been talking about, which has everything to do with free fall, right? And so it has some velocity, and that velocity is that acceleration downward is constant because of gravity, right? So I'm just going to come up with a hypothetical situation here. So when we're right up here at the top, the initial velocity on the y would have to be 0 meters per second at that one instantaneous point. So if we know that we have our coordinate system, right? We're always supposed to draw our coordinate system, right? So if you've got a graph, if you're in math class, and I'm just making this curve up, right? So you've got this curve that you're looking at. And let's just say you take this point right here. Okay? At that instant, that tangent line, at that instant, you know something about that object. Well, if I've got this parabolic motion right here, then what I know is this, is that at that point in time, at that instant, there is something happening. So for a very brief instant in time, the clock starts, and it's now on the second half of its journey, and initially right there, that velocity is 0 meters per second. Okay? So now let me erase this stuff down here. Go back to my blue. All right. So as this thing, I'm gonna put this right here, and I'm gonna put this right here. All right. So now I'm gonna also mirror that on both sides. I'm gonna mirror that on both sides. Just try to make a point here. If I call this velocity 1 and I call this velocity 2, obviously up at the top, velocity 3, so this would be velocity 4, velocity 5, all right? Here is my initial velocity, and then obviously this is my final velocity. I could have said 1, 2, 3, 4, 5, 6, 7. I mean, I could have done whatever. I could have made the initial velocity v1, and where I have v1, I could put v2. Where I have v2 right now, I could have put v3. I just chose to mark them this way because we're used to talking about initial and final velocities. As soon, whatever the velocity is when this thing is kicked, as soon as it hits the ground, then the initial velocity is going to equal the final velocity, except the final velocity would be negative, so it's going to have to equal the magnitude of that final velocity. Because once we get to the top of the arc, the velocity, all the energy that is transferred from here to the top, it then begins again. If it's at 0 meters per second up at the top, then it's going to start picking up that speed on the way back down. When it's initially kicked, it's going to have it's going to have all of its velocity, but when we get to the V1 on this, it's slowed down a little bit. It's a little bit less. It's a little bit less. And when we get to V2, it's a little bit less. When we get up there at the top, it's for that instant at 0 meters per second. But then, if you think about it, if we take this one side, this left side, and we flip it over, and we mirror it, and what I'll do is, to mirror it, I will take a different color. The second half here is equivalent to the first half. The only difference is the magnitudes are a negative value because it's traveling downward. That's the only difference. That is the only difference. So that means that the velocity at 1, if we look at this right here, it would be equivalent. So the velocity at 5 would be equivalent, but it would be negative. So there we go. Velocity at 2 would have to equal the velocity at 4, but that is it's downward. I think that's kind of pretty straightforward. And then again, when we're along the x-axis, right? So the velocity along x has to be the change in x over the cosine of theta times delta t. So the displacement that we would measure along the x-axis would have to be equal to whatever the velocity on x is times cosine theta times delta t. That's going to be helpful for what you're going to want to do when you're figuring out your problems. And again, remember the vertical component is going to be the same as it has always been. Change in y, vi. So since this is at an angle, whatever sine theta is, times delta t plus 1/2 a delta t squared. All right, so take this information, go apply it to what we've been doing, work out some of those problems, and as always, I'll post some problems. I'll post the solutions for you so you can take a look. All right, hope that helped. Always good seeing you. Go do some physics problems. We'll talk soon. Bye. There it is. So as you saw, this thing is going up along a path and it's arcing its way back down. But when it gets to the top of that path, for that one brief instant in time, it's, if you think about it, all the way over here, however much time that takes for horizontal displacement, and if we go back at the top of that arc, that must be half of the amount of time that it takes, half the amount of time to get to the topmost point of its arc, and the same amount of time to reach back down on the ground. Regardless of the velocity at which it was launched, this is going to hold true. All right, we just have to evaluate both the y and the x components correctly, knowing what our angle is. And if we don't have the angle, as long as we can resolve the rest of our components in some way, then we can always figure out the angle, as we learned back in lessons dealing with vectors. So keep that in mind. We're just bringing all these kinematic and all these vector formulas and stuff together so that we can better evaluate all the little aspects of what goes on in our lives. It's always good to see you. Stay curious, do some practice problems. I'll be here, and I will see you soon. Fun as always.